So here we've got two parallel plates of charge, positive and negative. And also in between them, partway in between, we've got a wire with current flowing upwards. And we're going to be launching a single proton at a time. We're shooting a proton downwards from the top at some specific distance from the negatively charged plate, so that it follows a straight path parallel to the wire. So somewhere, we don't know where yet, we're going to be launching a proton. And let me just draw that as a circle. Somewhere we've got this proton. And we want this proton to be able to move straight down. We just want to follow a straight path parallel to the wire. And also it's moving downwards. So let me mark the velocity there. So there's this proton and its velocity. And I think do we know its velocity? Yeah, its velocity 5 times 10 to the 7th meters per second. So ludicrously fast. That's like more than 1/10 of the speed of light. But it's moving, and we want to make sure it's moving in a straight line. And what's the only way an object can move in a straight line? If it's moving in a straight line, what does that tell us about it? Yeah, net force equals, constant velocity. Actually, it doesn't specifically say it has to be constant velocity, it's just moving in a straight line. So it might be speeding up or slowing down. There might be a force with the motion making it speed up, or a force against the motion making it slow down. But we at least know there's no side-to-side force. If there was any horizontal force, that would cause the object to divert onto a curved path. Straight line path means there's no sideways force. There might be force up and down making it get faster or slower, but we know there's no sideways force. So we could say, for instance, that we know that there's no acceleration horizontally, no side-to-side acceleration. So the sum of the x components of forces equals 0. And with that in mind, what forces could be acting on this object in this situation? Yeah, we should be considering both the magnetic forces and electric forces, because this is a charged particle, so it could be experiencing electric force if there's an electric field. And it's also a charged particle that's moving, so it could be experiencing magnetic force if there's a magnetic field. So let's investigate both of those. Presumably there will be some sort of electrical force. And typically you can calculate electrical force. What causes an electrical force? If you've got a charged particle, it's going to experience an electrical force if what is happening? What has to be existing in order to cause an electric force on this charged particle? Yeah, there's got to be an electric field. An electric force on a charged particle is caused by an electric field, and specifically it's just the charge of the particle, the charge of the test object, times the electric field. So let's see if we can figure out the electric field, because if there's an electric field in this region, we should expect an electric force. And in this region, between the charged plates, we should expect an electric field in which direction? Yeah, to the left. Generally, if you've got positive and negative charges involved as source charges, and we're treating the plates as source charges here, you should expect electric field from positive towards negative. So we should expect electric field lines from the positive plate towards the negative plate. And because these are large parallel plates, we should assume constant electric field in the in-between region. We get a strong constant electric field from the positive plate towards the negative plate in between, and basically no electric field outside. or at least a very weak electric field outside. So if we got electric field to the left, what should we expect the direction of the force to be? Yeah, also to the left, because the electric force is electric field, which is to the left here, times the test charge, which is positive. You multiply a vector by a positive number, and you get a vector in the same direction. So we should be expecting a force to the left. Let me draw that in here. So you've got an electrical force to the left. Which means if we want to make sure that there's no net force sideways, we're also going to need a magnetic force in what other direction? Yeah, we want a magnetic force to the right, because we want the forces to cancel each other out. We wanted the total sideways force to be 0. And the magnetic force is going to be caused by a magnetic field. So let's investigate the magnetic field here. What object in this is acting as a source of the magnetic field? Yeah, the wire has current. Current is flowing charge. That's going to create a magnetic field. And how would we determine the direction of that magnetic field? Yeah, we use the right-hand rule, and we got to be careful about out of the page, because we're talking about, I guess in this region, it would be out of the page, right? You point your thumb in the direction of wire and curl your fingers wrapping around the wire. On the left side of the wire, your fingers are pointing outwards. So on the left side, we have an outwards magnetic force, or sorry, outwards magnetic field, I should say. So an outwards magnetic field and how would we use that to figure out the direction of the force? If you know, yeah, we could use the second right-hand rule. In particular, you could use the 3-finger version. You point your thumb in the direction of the motion of the particle downwards, and your index finger outwards, because that's the direction of the magnetic field. And now your middle finger is pointing to the left. So that means this object would experience a magnetic force to the left. Is that what we want? No, we don't want these forces to combine and make a strong force. That's going to make the object curve off in one direction. So we're going to have to do things a little differently. In fact, in order to make this work, how is it to the left? You can use the second right-hand rule with the 3-finger version. So you want to be able to hold your fingers perpendicular to each other, making a essentially XYZ plane or XYZ axes. You point your thumb in the direction of motion of the particle. This particle is moving downwards. You point your index finger in the direction of the magnetic field out of the page, and your middle finger should tell you the direction of the force. Or if you have difficulty holding your fingers perpendicular to each other, you can also point your thumb in the direction of the motion of the charge. Point all your fingers straight in the direction of motion and imagine the palm of your hand pushing on the object. That is the direction of the force to the left. But we don't want a force to the left. We want a force from the magnetic field to the right. So that means we're going to need magnetic field in which direction? Yeah, we're going to need an inwards pointing magnetic field. Is there any other location where we would expect an inwards pointing magnetic field? Yeah, if you go to the right side of the wire, again, using the first right-hand rule, point your thumb in the direction of current and your fingers wrap around. On the right side of the wire, the magnetic field is pointing into the page. So everywhere in that region, we've got this inwards pointing magnetic field. And that's the direction we want. Because if we put this same particle over here, Now, if we try the same second right-hand rule, point your thumb in the downwards direction, point your index finger outwards, and your middle finger should be pointing to the right. So if we put the charged particle in the region that has an inwards pointing magnetic field, we get a rightwards pointing magnetic force, and that's exactly what we want. So you've got this magnetic force to the right. So putting the proton on the right side of the wire and moving down gives us the opportunity to have these forces cancel out, because this at least means they're in the same direction. Any questions on that so far? So by putting the particle on the right side, we've established that the directions are opposite. But in order to cancel out, so we get no horizontal acceleration, we need the directions to be opposite, and what else has to be true? Yeah, they've got to be equal magnitudes. So what we need to do here is assume that the magnitude of the electric force equals the magnitude of the magnetic force. If that's true, and the directions are opposite, which we already established, then the forces cancel out and the object is experiencing no horizontal force, and it can just keep drifting in a straight line. We know the magnitude of the electric force is just Q times E. What about the magnetic force? Do you have any formula for how strong you would expect a magnetic force to be? Yeah, QVB sine theta. Although in this case, what's the angle between the velocity and the magnetic field vector? Yeah, 90 degrees, and sine of 90 is just 1, so we can ignore that. So QVB, we can fill that in for magnetic force. And then what? If we want Q times E to equal Q times V times B, what can we do with that? Yeah, we could solve for E by dividing both sides by Q. In fact, if we divide both sides by Q, what's going to happen? Yeah, those cancel out. And that's convenient. It means we don't actually need to worry about what the charge is. In fact, it doesn't matter whether this is a proton or some other particle. In fact, it doesn't even matter whether it's positive charge or negative charge. Charge cancels out, so it doesn't matter one bit what this charge is, as long as there is some charge. We're left with electric field must equal speed times magnetic field. So that's what has to be true in order to allow this particle to continue in a straight line with no changes. The electric field must equal the speed times the magnetic field. We know the speed, 5 times 10 to the 7 meters per second. Ideally, we'd like to figure out where the particle has to be in terms of distance. So is there any way you can write out expressions for the electric field here or the magnetic field here that might relate it to where the particle is? Do you have any formulas for how strong the electric field should be or how strong the magnetic field should be? KQ over R squared, that's going to work anytime you're talking about the electric field from what sort of source? Yeah, from a point charge. Electric field, at least magnitude of electric field, equals K times Q over R squared if the source is a single point or small enough and we're far enough away from it that we can treat it as a single point. Is that the case here? Is the electric field being caused by a single point charge? No, we've got these giant plates of charge. So we can't use KQ over R squared here. There are formulas relating the charge density, like how much charge per square meter to the electric field, if you're talking about parallel plates. But we don't have the charge density here either. We don't know how concentrated the charge is. What's the only thing we do know about the electric field situation here? Do we know anything about these plates? I think that's for the magnetic field, right? Magnetic field equals mu naught times current divided by 2 pi r. So let's go ahead and start there. We know that the magnetic field strength, specifically the magnetic field caused by a current in a wire, which is what's going on here, is mu naught times current divided by 2 pi r, where r is the distance from the wire. And we have the current here. The current is 2.77, and location is really what we're trying to find. So let's label that. Let's just call this distance, let's just call that distance r. So r is how far the particle is from the wire. Let me just establish a variable there. Yeah, I think that's also going to be useful. We've got some unknown distance from the wire, so we can write out the magnetic field in terms of that. And also, yeah, electric field is the derivative of voltage with respect to position. This is a very important relationship between those quantities. We haven't really talked about it very much, but the idea is that the electric field is related to voltage. Electric field is the derivative of voltage with respect to distance. So a strong electric field means the voltage is changing lots, not lots per second, but changing lots per meter. So for instance, if the electric field is very strong, then 2 points that are 1 meter apart from each other are very different voltages. If the electric field is very weak, then these 2 points that are 1 meter apart from each other will be mostly similar voltages, not very different. And if there's no electric field, if the electric field is 0, then there's no difference in voltage from location to location. Differences in voltage involve the electric field and the distance. So you can write this in 2 different ways. You could say that the electric field is, at least the magnitude of the electric field, is the absolute value of derivative of voltage with respect to x. That is, how strong the electric field is all about how quickly the voltage changes from location to location. Or you could write it the other way. You could take, what's the opposite of a derivative? Yeah, the integral. The voltage is the integral of the electric field with respect to position. And formally, there's a negative there as well. In fact, let me just put in the actual signs. The electric field is the negative derivative of voltage. The negative in this case signifies that the electric field is pointing towards lower voltage. Or alternatively, you can write the voltage as the negative integral of electric field with respect to position. So electric field is talking about how much the voltage changes per meter, or you could say voltage is talking about how much electric field accumulates as you travel from location to location. In fact, this is very similar to something you've seen before. If we multiply both sides of this by charge, what's charge times electric field? Yeah, that's the force. And what's charge times voltage? Right, so we get force equals negative derivative of potential energy with respect to x. And that's exactly the relationship we were looking at way back in 7a, that force is the derivative of potential energy. If you've got some sort of graph of potential energy, the slope of that potential energy graph tells you how much force there is. And the negative sign just means the force is pointing towards lower potential energy. This equation here relating electric field and voltage is exactly the same structure. It just is missing the times charge. The idea is that just like force is talking about the slope of potential energy, likewise electric field is talking about the slope of voltage. If you have a graph of position versus voltage, the slope of that graph is the electric field, but also with a negative, talking about the opposite of. the idea there is that the electric field is pointing towards lower voltage zone, just like force should point towards lower potential energy. So this is ultimately how electric field and voltage are related. They're related in the same way that force is related to potential energy, because electric field is really just force with the charge divided out of it, and voltage is just potential energy with the charge divided out of it. Any questions on that so far? And I put together a chart a while back, just describing those quantities and how they're related. Let me paste a link to that into chat. If you go to math.ncheese.org/P7C/electricquantities.pdf, that's just got a chart of these 4 important quantities: force, electric field, voltage, potential energy, showing briefly what they mean and how they're related to each other, how to convert back and forth. Any other questions on that so far? So let's see if we can actually make that calculation. Specifically, we know something about voltage here. We know there's a difference in voltage between these locations. We know that if we look at the difference between these locations, from here to here, the difference between the plates is 90 volts. And by the way, I don't think we're going to need it for this problem, but in case we needed to know, which one of the plates would you expect to be higher voltage? Yeah, the positive plate should be higher voltage, the negative plate should be lower voltage. And note that that matches up with the idea of the electric field. The negative sign in this equation means the electric field points in the direction of decreasing voltage. Electric field's pointing towards the left. So as you move to the left, you should expect lower and lower voltage. We've got a high voltage, then lower voltage, lower voltage, lower voltage, and then very low voltage. And typically in a situation like this, if we needed to label voltages, we'd probably call the middle 0 volts. The positive plate would be positive 45 volts. The negative plate would be negative 45 volts. So there's a difference of 90 volts. But in this case, we know there's a difference of 90 volts overall across how much distance? Yeah, distance of 1.3 meters. So if we fill in, technically we're finding the average electric field here, delta voltage over delta X. The difference there is that the derivative, dV over dx, tells you how much the voltage is changing right now, right at this location. Whereas delta V over delta X, the total difference in voltage divided by the total distance, technically this tells you the average electric field in that region. But we're assuming the electric field is uniform, a constant electric field everywhere. So the average electric field is the electric field everywhere in this case. And if we actually divide those, delta V, 90 volts, delta X, 1.3 meters. If you divide those, what do you get? Yeah, 69.2, and that's volts over meters. But volts over meters is the same as newtons per coulomb, which might be a more useful way to write it here. So that's our electric field, 69.2 newtons per coulomb. And again, technically that's an average, but since the electric field is the same throughout this entire region, the average is the value everywhere. So we now know the electric field. Electric field, we can fill that in here. We also know the speed. That's given as 5 times 10 to the 7 meters per second. So at this point, we just need to fill in the formula we have for magnetic field and see what we can do with that. Any other questions on that so far?
I had a quick question.
Mhm.
So with the average electric field, do we need to consider the negative sign or no?
No, because we're just looking for magnitude. The negative sign here is really
Okay.
talking about direction, saying that the electric field points from the high voltage zone to the low voltage zone. But we've
Okay.
already established the direction, so we're just looking for magnitude. Any other questions on that so far? So we know electric field magnitude, we know the speed that was given at the beginning, and we can also replace B with this formula, since we're talking about the magnetic field caused by a wire. So let's try that. E equals V times that whole formula, mu times current divided by 2 pi times radius. So that's what has to be true here to make those forces cancel out. The electric field must equal, and we know the electric field, that must equal speed times universal magnetic constant times the current in the wire divided by 2 pi times the distance from the wire. And of all those parameters, what are we actually trying to solve for here? Yeah, we want to know radius. We want to know where the object has to be. And note that where the object is doesn't influence the electric field here. The electric field is the same in this entire in between the plates region, but it does influence the magnetic field. So how could we isolate R here? Divide V. The thing is, R is in the denominator. Before we get rid of the V, the mu, the I would start by getting R out of the denominator. And how would you do that? Yeah, I would start by multiplying both sides by R. Exactly. Multiply both sides by R and divide both sides by E. Because if you multiply by R, you get RE equals V mu I over 2 pi. And then we can just divide both sides by E. So R, the distance, is going to be V mu I divided by 2 pi E. So that should be a formula we can use to find the R, the distance from the wire itself. And we can plug in these numbers. We're given the speed, 5 times 10 to the 7 meters per second. Mu you can look up. That's just the universal magnetic constant. It should probably be on the formula sheet. I is the current, which is given as 2.77 amps, 2 pi, and then the electric field is what we calculated over here, 69.2 newtons per coulomb. And as long as everything in here is in units of kilograms, meters, seconds, newtons, coulombs, joules, that should work out to just meters. That'll tell you the distance from the wire. Although technically the problem is asking not distance from the wire, but distance from the negative plate. So what else would we need to do once we found the value of R? Yeah, just add that 0.6 meters, because we've got 0.6 meters from the plate to the wire plus an extra R, whatever R works out to be. That'll be the distance, the location where we can just send a particle straight down and it'll continue moving straight down because all the forces cancel out. Any other questions on that so far? Or any other questions on these electric fields and magnetic fields? All right, and I think someone was also asking about the, what was it, problem 1 on interference. Yeah, let's take a look at that as well. Okay, so here we've got several speakers, and we're trying to figure out what's our goal here? What are we trying to figure out in this situation? Yeah, we want to find the chair that has the most sound. And that's going to be related to distance. But this is ultimately about interference. I mean, technically, yes, the further you get from the source, the quieter it's going to be. But this one specifically says ignore any decrease in intensity of the waves as they propagate within the room. We're not talking about getting quieter as you get further away. We're talking about loudness and quietness as a result of interference. So if we want the most intense sound, what type of interference should we be looking for? Yeah, we want constructive interference. So let's see if we can find that. We can start with the usual formula for total phase difference. The idea that we have the time term, the distance term, the phase shift term, all adding up to the difference in total phase, capital Phi. And let's fill in some of the values right now. Are there any terms in this that we know we can ignore? Yeah, they're the same frequency, so delta F is 0. And yeah, we can just leave out that entire first term. No difference in frequency. Is there a difference in path length? Yeah, like for instance, if you're standing in chair A, you've got wave 1 traveling this far, wave 2 traveling this far. Those are different distances, x1 and x2, so there is a difference in x. What about wavelength? Is there any difference in wavelength? Shouldn't be, right? They're the same frequency, they're traveling at the same speed, so they have the same wavelength. That means wavelength is a constant, so it can be factored out of the delta there. We've got 2 pi times delta x divided by the wavelength. What about phase shift difference? Is there any difference in phase shift between 1 and 2? Probably not, right? Because it specifically tells us, in part A at least, the speakers are wired in phase. So we know there's no difference in delta little phi. As not to be confused with delta capital phi, the difference in total phase. But we can at least say the difference in little phi at the source is 0, which means the only contribution to the difference in total phase is how far the waves travel, or the difference in how far they travel. We end up with just negative 2 pi delta x over lambda equals delta total phi. And what type of interference? Actually, we're looking for which one has the most constructive. So I think we should probably be treating delta phi as an unknown for now. If we were specifically looking for exactly constructive, I would set delta phi equal to a whole number multiple of 2 pi. But in this case, we don't know which one it is. We're trying to figure out which one is constructive or at least closest to constructive. So I would just calculate negative 2 pi delta x over lambda for each one of these and see what we get. Do we know the wavelength here? Or can we find the wavelength? Yeah, we can use the usual velocity equations. Speed equals wavelength times frequency. Therefore, wavelength equals speed divided by frequency. And what should we use as the speed of sound here? Yeah, I think we're assuming 340 meters per second. And then it tells us the frequency is 170 hertz, which is 1 over seconds. Seconds and seconds cancel out. We're left with meters. And I think that's just going to be 2. So the wavelength here is just 2 meters. And we can fill that in. Wavelength is 2 meters. And then I think we can just calculate delta x for each one of these individually because it tells us the distances. Like for instance, for chair A, I think it tells us these distances, 1.5 meters from speaker 1 and 2.5 meters from speaker 2. So let's just calculate each of those delta x's. And we'll need to be careful here about direction because you want to make sure you're subtracting in the same order the whole time. So do you want to subtract 2 minus 1 or 1 minus 2 here? Sure, 2 minus 1. Every delta in this problem, we're going to use 2 minus 1. And of course, it doesn't really matter which order you subtract in. You just want to make sure you're consistent about it within a problem. So let's just write here as a note to ourselves, in this problem, every delta is going to be something about speaker 2 minus something about speaker 1. And then let's calculate each of these. For chair A, 2 minus 1, we know chair A is 2.5 meters away from speaker 2, 1.5 meters away from speaker 1. So if you subtract those, what do you get? If we've got 2.5 minus 1.5, yeah, it should just be 1. So for speaker A, the distance, the difference in distances is 1 meter. And what about for speaker B? If it's 3 meters away from speaker 1 and 1 meter away from speaker 2, 2 minus 1 would be 1 meter minus 3 meters. So what would that be? Yeah, negative 2 meters. And note that this is really where the direction is important. Subtracting, or the order of subtraction determines whether the result is positive or negative. In this particular problem, that's not going to matter because you've only got one term and it doesn't really matter whether it's positive or negative. But if you're combining that with another term, like if there was a phase difference, then that would be important. And I think the next part of the problem, part B, does involve a phase difference. So it's a good idea to keep track of that. What about for C? What's the difference in distance there? 5 meters versus, yeah, subtract 2.5 minus 5. That's going to be negative 2.5 meters. So we've got all 3 delta x's. And now we can just plug each one of those into this equation individually. So let's try each one of those. We replace delta x with 1 meter. And what does that reduce to? Yeah, negative pi. And negative 1 pi, what type of interference would that be? Yeah, that should be destructive because 1 pi is half a cycle offset. And for the total, positive or negative doesn't matter. Negative pi or positive pi, that's half a cycle. Half a cycle offset either way means you get destructive interference. So that's going to be complete quiet. That's going to be essentially no sound at all. Assuming wave 1 and wave 2 are the same loudness. If they're exactly the same loudness, they'll cancel out. If they're different loudnesses, different amplitudes, they'll partially cancel out, but not completely. But they'll at least be canceling out as much as they can be. For chair B, we fill in delta x, which is negative 2 meters. And what does that reduce to? Yeah, positive 2 pi, which is what kind of interference? Yeah, so that is going to be the loudest possible sound. Presumably that's the answer part 1A is looking for, loudest sound in chair B. We should probably check chair C also in case that might also be constructive. Chair C, we fill in negative 2.5. And what does that reduce to? Yeah, negative 2.5 pi. Or I guess that is positive. Again, the positive or negative doesn't really matter. In this case, 2.5 pi is, would that be, yeah, that's going to be partial interference because it's neither a whole number of cycles nor something and a half cycles. It's somewhere in between. So it looks like A is going to be dead silence, C is going to be slightly loud but not very loud, and B is going to be the loudest. Any questions on that so far? And then I think part B introduces, yeah, part B introduces a phase difference. And this is why I wanted to be very careful to keep track of the positive and negative signs here and keep track of which order we're subtracting, because part B introduces a phase shift. We do have a difference in phase. So that means we got to be very careful to keep track of positives and negatives. It looks like speaker 1 is delayed. Speaker 2 gets a head start. So like speaker 2 emits a crest, and then a quarter period later, speaker 1 emits the same crest. So speaker 1 has a delay. Speaker 2 has a head start. And if we subtract 2 minus 1, first of all, it's a quarter period. A quarter of a period is how much in terms of radians? Pi would be a half cycle because one full cycle is 2 pi. Yeah, pi over 2 should be a quarter cycle. So if we're talking about a quarter of a period, that suggests a phase difference in little phi. Yeah, quarter period or a quarter cycle. And it's talking about it in terms of time. But instead of looking at the time term, it's going to be more useful to look at the phase shift term, because phase shift difference is all about whether these sources are in sync with each other or not. And here, they're not in sync with each other. They're offset by a quarter period. So pi over 2. And we got to be careful about whether it's positive or negative pi over 2. In this case, we're subtracting 2 minus 1. Speaker 2 gets a head start. Speaker 2 is ahead of speaker 1, so I would assume speaker 2 has a larger phase shift, larger lowercase phi. And then 1 has a smaller value. So 2 minus 1, that's going to be a larger value minus a smaller value. So we should expect a positive. If we were subtracting in the other order, 1 minus 2, this would be negative pi over 2. But the important thing to remember, I think, is that the one that's ahead, the one that has a head start, is going to have a larger value for little phi. And since we already did the calculations for the 2 pi delta x over lambda term, we're just going to have this extra term for the plus delta phi. We can keep everything else we've already got. We've got the negative 2 pi delta x over 2m, 2 meters. We already calculated that for each chair. We just need to add an extra plus delta phi to each one. And since delta phi is pi over 2, we're just going to add in an extra pi over 2. So we can do that just to the end results. We just add in an extra plus pi over 2. Plus pi over 2. Plus pi over 2. To see what we get there. So if we add pi over 2 to each of these to account for the extra caused by this quarter period delay, what do these become? Negative pi plus pi over 2 would be what? Yeah, or technically negative pi over 2, but again, the sign doesn't really matter. The sign of the end result doesn't matter, because negative pi over 2 is what kind of interference? Yeah, that'll be partial. And then share B, 2 pi plus pi over 2 would become 2.5 pi. And that's also partial because it's not a whole number of cycles, and it's also not something and a half cycles. What about chair C though? If we add 2.5 pi plus an extra half pi, what do we get? 3 pi. And what kind of interference is that? Yeah, that's now going to be destructive. So if we modify this by adding in that extra phase delay, then chair A and B both switch to equal amounts of partial interference. Those are both going to be halfway between constructive and destructive. But chair C goes completely silent. Any other questions on that? All right, then that's it for today. Good luck on finals, and I will see you at the review session tomorrow. You're welcome.